My name is QUAN, student from 4 BEKU Section 3, and this video is going to explain my final year project with the title of Investigate the Influence of PID Setting towards the FPV drone flight performance. And my supervisor is SAIFUZAM bin JAMRI. The first chapter is the introduction. Main aerial vehicle, which is the UAV, is categorized for drone, robot planes, and any aircraft that does not require pilot on the vehicle. One example of UAV is a FPV quadcopter, which is the first-person view quadcopter. For example, most aerial photography is using the FPV quadcopter to film. Thus, the stability is very crucial for the drone to avoid the player feeling panic because the driver can only control the drone with the view from the drone. To make sure the drone more stable, PID is required to apply and tune for the FPV drone. So the second is the problem statement. As mentioned before, stability is the most important requirement for a drone. Unstable flying can explain by the gyro is unable to follow the command from the player immediately. This may be caused by the wind or any unbalance of the propeller, and this problem will lead to the motor overheat and oscillating. Let's come to the objective and scope. So the objective is to study the type of FPV drone, assembly a complete FPV drone to investigate the flight performance, investigate the influence of PID parameter towards the FPV drone, and the final is tuning and verify a better PID for parameter for the FPV drone. Next is about the scope. So a DIY version of FPV drone called a EASHIN Tyro 79 is selected for this project. Soldering and wiring skill is required when assembling the drone, and some extreme movements are required to perform, like the sharp turn, 360 degree of flip, and low throttle. And all of this flying record is analyzed by using Black Box Explorer. And the PID gain value is tuned by using the Betaflight configurator. The second chapter is the literature review. The first one is the PID controller. The proportional is the simple gain which is used to minimize the error between the output and the reference. Besides, proportional also affects the time response of the system. The integral is mainly focused to compensate the steady-state error and assist with the proportional to minimize the error. And the last one is the derivative. So the derivative is to reduce the percent overshoot that caused by the proportional value, and meanwhile creating the noise to the system. The FPV drone is fast, can perform any movement, and does not require GPS, which means it can perform any freestyle anyway, but only with low battery sustainability. Cinematic drone is slow and have limited movement, which is also require the GPS to fly, but the battery sustainability is very high and also stable. The third chapter is the methodology. So this is the flowchart for the whole project and separate into PSM1 and PSM2, whereby the PSM1 will focus on hardware assembly and the PSM2 will focus on software tuning. And I will provide the slide as a reference in the description below. The hardware accessory required to assemble a FPV drone. So there are total 10 hardware is required to complete an FPV drone. So apart from the hardware, the software includes BL Heli configurator, which is used to manage the setting of the ESC and the motor. Next, the Betaflight configurator, which is used to manage most of the setting of the FPV drone, like the PID setting, channel, on-screen display, which is all SD, black box, and also the control mode. And the last software is the Black Box Explorer, which is used to review the flight record and also the analysis purpose. Now, I'm going to explain the action required to perform by the drone to investigate the flight performance. So the first one is the sharp turn. So the drone will start to increase the speed and until the end of the corner, and then have an emergency turn at here, and then return back to the original position, and then start to landing. The second is the low throttle. So the drone is fly vertically to a high altitude and then turn into free fall status, and then increase the throttle immediately to let the drone stable in the air and then landing. The third action is a 360-degree of flow, which is the full turn of the roll axis. Same goes to the fourth action, 360-degree of pitch, which is having a full turning of pitch and then landing. So after understanding the action, now I'm going to explain the general problem when flying. The first one is the prop wash. So an oscillation is happen during the end of the sharp turn, like this, the oscillation, which is called as prop wash. So this can be observed by the action of sharp turn and also the low throttle. The second is the Bowspec problem. So this is the problem when a Bowspec is created after 360-degree of flip. Okay, so let's have a slow-mo. So this oscillation is a Bowspec problem. After understanding the action and the problem, so this is a flow chart for the tuning process whereby the prop wash is fixed by the P and D parameter and the Bowspec problem is fixed by the integral parameter based on the research. Now is the fourth chapter, which is the result and the discussion. In this chapter, I will compare the influence of flight performance when applying the best PID value and the low PID value. The best PID setting can be explained as a high PID setting due to all the PID parameter is being higher than the initial PID setting. So each action is classified into two axes, which are roll and pitch axis for the investigation. So let me explain the graph first. So this is the result of the low throttle action towards the roll axis. On the left side is a high PID value and on the right side is the low PID value. Okay, for the above part, the red color result is a gyro response, which is the response from the cop quarter. And for the purple color is the RC command, which is the stick command from the player. Okay, for the yellow color here is a throttle level of the stick command. So the throttle is from 0 and increase suddenly to allow the drone stay in the air. So before here is a free fall status and here is a landing status. Okay, for the bottom part, the yellow is represent the proportional, the green color is represent the integral, and whereby the blue color is representing the derivative. So back to the analysis, for the high PID value part, the gyro is facing a small oscillation at here when the throttle level is suddenly increased, which means a small prop wash is happening at here. So the RC command is keep unchanged due to the roll axis supposedly did not having any changes on the stick command, which means the oscillation created by the gyro is an unwanted movement. For the PID part, the increasing of the proportional at here is represent that the proportional is trying to allow the gyro to follow the RC command. The integral have a large change at here during the 1 second to allow the gyro balancing in the air. Okay, so for the derivative is keep oscillating due to there is no being overshoot that created by the proportional parameter. Okay, for the low PID value part, the prop wash is going worse which can be observed by the large oscillation at here. So on the PID side, the proportioner is trying to decrease the error between the gyro and the RC command, and obviously this is not enough gain to solve it. So the integral is hugely increased to assist the proportioner for the balancing the drone at here. So the derivative should assist the proportioner to avoid the overshoot happening. For the pitch axis, same result is found where the high PID value have a smaller prop wash problem comparing to the low PID value, whereby the low PID value have a very serious prop wash problem. So the integral and the proportional at here is assist each other to decrease the prop wash problem, and the derivative is also avoiding the overshoot problem. So on the other side, the integral and the derivative obviously did not assist with the proportional to balancing the drone, and the only increasing of the proportional parameter was unable to eliminate the error and keep oscillating. So this is the result of 360 degree of roll, and all the result is analyzed based on the roll axis only. So the gyro is start to rotate from here, and then finishing the rotation and back to the initial flying status. So same goes to the red color, is represent the gyro, and the purple color is represent the RC command. So the Bowspec problem can be observed by the overshoot at the end of the rotation at here and also here. Okay, so an obvious Bowspec can be observed for the low PID value, and for the high PID value, the Bowspec problem can be ignored because there is no overshoot after the rotation. So for the high PID value, the proportional is increased gradually to allow the gyro follow the RC command, and the derivative is doing good to avoid the overshoot created by the proportional. So there is no overshoot at here. So this parameter is allow the gyro attached with the closely to the RC command, which can be defined as the desired movement. So for the less PID part, there are two undesired movement, which is happening at here and also here. So the gyro is obviously cannot follow the RC command, which created the overshoot at here and also here. So the derivative cannot avoid the overshoot problem caused by the proportional, which lead to the undesired movement. So the error should be decreased like the result of high PID value by the tuning process. So at the end of this video, I'm going to conclude and give some recommendation. A DIY version of FPV drone is analyzed and assembly successful for the tuning purpose. The software and hardware is conducted successful for FPV drone to investigate the influence of PID towards the flight performance. This set of best PID setting is only specialized for this FPV drone, only due to each FPV drone has a different hardware and different flying style of the player. Thus, the tuning proposed is highly depending on the requirement of the player. For the recommendation, a recordable camera is highly suggested to use when the tuning process, because the prop wash and the Bowspec problem can be observed easily through the video. Besides, the indoor location is suggested to test the flying when tuning, which can avoid a lot of external disturbance like the wind. Again, the tuning process is only let the player feel comfortable and suitable when flying. Hence, do not follow any PID setting from others' drone. Tune yourself.